Welcome to Lyons Township High School, AP Physics. Today we got an example involving wave superposition, or when two waves are striking each other and interfering. This example will involve no math and no equations. So what we're going to do is we're going to look at this point and we're going to graph a couple of things. So the first thing we're going to graph is what will happen to this point. Let's say it was a bobber, and let's say these are water waves. And these water waves had the same wavelength and they had the same amplitude. And they're going to go the same speed toward each other. Now, having said that, a quick note, this is actually three waves, right? 1, 2, 3, and 1, 2, 3, okay? So as these waves or water waves crash into each other, if this were like a fishing bobber or a piece of wood, what would happen to it over time? So if I were to videotape this little fishing bobber, what would I see on the video? Okay, so we're going to graph the vertical position of that fishing bobber versus time. Okay, and I tend to find it's easiest to look like as the waves combine, like every half wave. Okay, so we'll start, they're coming toward each other and they combine so that there's half a wave overlapping. You have this crest of this right-hand wave being the trough of the left-hand wave. Okay, and you'll notice a couple things. We're only looking at that point, and at that moment you have a crest and a trough meeting. And if you'll recall, the waves can have constructive or destructive interference. Constructive interference means you either have a crest meaning a crest makes you a big crest, or you have a trough meaning a trough gives you a big trough. That's not this, right? So in this case, we have a crest and a trough meeting. That is destructive interference. They're temporarily destroying each other. So basically, that bobber wouldn't move. It would stay flat in the water. So if you were videotaping that fishing bobber, it wouldn't move, okay? Now we'll go until these overlap one full wave. And now we got two equilibrium points meeting, which means the fishing bobber still hasn't moved yet, okay? And for kicks, we'll go 1.5 waves. And you'll notice we have a crest meaning a trough again. So what's going to happen to this bobber over time? Well, it's going to be absolutely stationary, okay? So if you were graphing this, would be pretty boring. You'd have a graph on the t-axis, horizontal, never moving, then the bobber never moves up or down, okay? Now, by the way, in Physics 1 here at LT, we actually do a lab in a ripple tank, and you actually have a pattern like this in several places. So you can actually see that the water remains flat in a place like this, okay? We would call this, in a ripple tank, we would call it a node. It's a place where there's little to no disturbance, okay? There are other places what we call antinodes where you get a lot of disturbance, okay? So if you graph the height of this bobber as a function of time, well, the bobber wouldn't move. Now, another kind of graph that we can make, though, is that was a movie. If you take a video of that bobber, it wouldn't move. A different thing we could ask you is when the waves have overlapped some, what is the height of the water at all different places versus position, okay? So that's a different kind of graph. So what we're going to do is we're going to look and see what the height of the water would be along this whole entire pattern versus position. And we're going to look when the waves are a half wavelength overlapped, a full wavelength overlapped, and then 2 full wavelengths overlapped. All right, so the waves come toward each other. Now here they haven't overlapped at all yet. Okay, so right now if you were to take a picture of the water, you would see 6 wavelengths in the water, okay? And then they're going to start overlapping. And I'm going to draw, now this is a different graph now. This is the height of the water versus where we're at. And we're going to make it so that half a wave overlaps, okay? So, all right, so there we go. Okay, that's half a wave overlapping. Now, you'll notice that again, the bobber is at zero height because you got a crest meeting a trough, they're destroying each other. But you also notice there's this whole area would be zero height. So between here and here, where the waves are overlapping, you have basically nothing happening, okay? And then to the right of this spot right there is just this regular wave, so it would look like, you know, crest, trough, or in this case, trough, or equilibrium. Let's see, trough, equilibrium, crest, equilibrium, trough, equilibrium, crest, equilibrium, trough, equilibrium. So it would go like this. You just basically, I'm just copying this down here, okay? And same thing from here to the left. Starting there, you've got a crest, equilibrium, trough, equilibrium, crest, equilibrium, trough, equilibrium, crest, equilibrium. It would look like this. There you go. So that would be, if you took a picture of these two waveforms, at the moment half a wave is overlapped, this is what you'd see. So you see this dead spot in the water, that there's no height, no wave or anything, and then you'd see the rest of each wave on each side of it, okay? So that would be if you had a half wave overlapped. What about if you had a full wave overlapped? All right, so I'm going to erase that. So we'll keep bringing these guys together until a full wave overlaps, like so. And I'm going to offset them just a little bit so we can kind of see what's going on there. So there you go. So again, we're taking a picture at that moment when one full wave from each waveform is overlapped. What do you got? So again, our bobber hasn't moved. You got equilibrium meeting equilibrium. That's at zero height. Okay. To the right of the bobber, you got a trough and a trough meeting. That is constructive interference. You get a big trough. And then you got an equilibrium position again. On the left, you've got two crest meetings. So you're going to have a big crest and then back to equilibrium again. So the part where the waves are actually interfering with each other, you'd see a big wave like that, one full wavelength. The rest of it would be, so starting from here, is just 1, 2 wavelengths of that wave. So you got, you know, crest equilibrium, trough equilibrium, crest equilibrium, trough equilibrium. So it looked like that. I'm just copying this down here. And same here, but you start with a trough. So trough equilibrium, crest equilibrium, trough equilibrium, crest equilibrium. Like that. There you go. So what you'd see is one big wave that's double the height. So if the height of these is 1, this would be 2. I'll even label it that way. So this would be 2, and then the rest of these would be 1 on each side. Okay. So you see one big wave, you'd see 2 wavelengths over here and 2 regular wavelengths over there. So that would be what you'd see if you had one full wave overlapping. What about if you had 2 full waves overlapping? Well, hopefully you can kind of see that what the pattern would be. Okay, so at that point, there's our 2 full waves overlapping. And basically, you'd have a couple things change. This would now be a big crest. This would now be a big trough. Okay, here you have a crest and a crest meeting. You have a big crest. Here you have a trough and a trough meeting. You have a big trough. All right, and then over here you have one regular amplitude wave on the left, and you'd have one regular amplitude wave on the right. So you can recreate that real quick. So if I took my picture right now, again, our bobber never moves, all right? But you have a big crest, equilibrium, big trough, equilibrium. Same thing here, big trough, equilibrium, big crest, equilibrium. Okay, so that would be the part where the waves are interfering with each other. You get 2 wavelengths. And then on each side, like here, you'd have a small crest, or small trough, small crest. And then over here, you'd have a small crest, small trough. Okay, so that would be what your wave would look like at that moment if you took a picture. All right, so that's if you have two waves of equal amplitude and equal wavelength, okay? What if we change one of those things? All right, so what we're going to do is we're going to replace one of these with this guy, all right? This guy has the same wavelength, okay, but he is double the amplitude. Hey, check it out. I'm waving at you. There you go, I'm waving at you. All right, so anyway,